Okay, we're going to continue on. Last time we pretty much wrapped up chapter 12, which again is the last chapter that is on our exam, which is Wednesday, if I remember to write it. But we're going to take that on Wednesday. Obviously, during lecture, we'll do that. I also posted up kind of a little bit more on molecular polarity and all that kind of stuff, a little short little video of a recording I did before that goes into maybe a little bit more detail than we got through. So make sure you watch that if you haven't done so. Just to kind of keep us on pace with the holiday we had, or a lot of holidays we have in this class, and obviously the exams and stuff are coming through. I did post a recorded lecture for chapter 8, which is for the next exam. Up there already, so make sure you do watch it. We're not going to officially kind of go through it, so we don't get too far behind in terms of where we need to be and stuff like that. So make sure that you do watch that. Along the way, we probably will talk a little bit more about some of the stuff in there, especially maybe the grams to moles type conversion, which we do a lot, obviously, in chemistry. But also, once you're done with that, the post-lab questions for the experiment 13, you can then turn in up there on Canvas, I think is maybe where I put it, I think. So make sure you upload those if you haven't turned those in as well with the experiment on the other day. Any questions on any of that stuff? So we're going to go to chapter 5, which is naming and nomenclature, which was supposed to be on this exam, but obviously did not make it. So like I said, probably after spring break, which I think is next week, right? Yeah. So after spring break, we will probably have some type of quiz on naming just by itself, and we'll kind of use that, I think, and we'll continue on like normal. All right, so let's get into naming. So when we talk about naming, it's really going to focus in on the two types of compounds that we talked about in bonding, which is ionic compounds, which, as we talked about, are again between a metal and a nonmetal. And in this situation, we always get a transfer of electrons from the metal to the nonmetal, as we talked about with bonding. And that is going to result again here in really cations being formed and anions being formed, which are positive and negative guys. And as we talked about, there's like, again, no sharing of electrons happening here. And that also is sort of a category in terms of naming, in terms of how to name a compound, is being able to identify as a metal and a nonmetal. And if it is that, you will sort of name it a particular way, which we will obviously talk about. Thank you. Now, the other type of sort of compound are molecular compounds, which basically are covalently bonded guys. And as we talked about covalently bonded, that's usually between two nonmetals. And here we do have sharing of electrons like we talked about there in our bonding chapter. Once again, the sharing can be equal, they could be unequal, but there is some aspect of sharing happening there. So kind of like we talked about with bonding, that, you know, one of the first things you want to try to figure out is what you're dealing with. Is it a metal or a nonmetal, or is it two nonmetals together? The same thing sort of goes with naming as well, because depending on whether it's a covalent compound or an ionic compound, there are different ways that you go about naming it. So again, sort of the same idea. You kind of want to think about what you got going on, and it will hopefully point you in the right direction in terms of how to name it. Now, when we talk about naming, there are certain things that we just roll with kind of common names. And H2O is one of those things, and it really should be called water pretty much in all cases. Nobody wants a refreshing glass of dihydrogen monoxide or anything like that, right? They would rather have a refreshing glass of water. It is not a trick question when you see that, yeah? So just put water and move on with your life, yes. Otherwise, I enjoy all the responses I get for that, but just put water. It's not really a trick question. NH3 is ammonia. That is also something that you see a lot in chemistry. It's actually a weak base, and you'll see it through other places, but we do call it ammonia. And CH4 is really your simplest sort of organic compound that you can have. And that's methane. So that's like the gas comes out when you light your Bunsen burner and all that good stuff out of the vent there. So when we name compounds, as I mentioned, there's really the two sort of categories at which we name them. And when we have binary compounds, they basically consist of two elements. And really, sort of that element identification of whether it's a metal or a nonmetal will point you in either, as we just talked about, the sort of ionic route of naming, or if it's two nonmetals, it will point you in that sort of covalent sort of route of naming. And again, there are differences in how we go about naming those guys. Now, when we talk about ionic compounds, they're also sort of broken into sort of two categories. And one category is a type 1 ionic compound, and one category is a type 2 ionic compound. So these are both, again, ionic compounds. And they will always contain a cation, which is our positively charged guy, and our anion. And when you write the formula, or you go to name them, it should always go in that order as well. So both in formula and when you go to name, you should always have the positive guy first, followed by the negative guy, again, when you write those formulas. To name these compounds, we simply use ions. So for example, the name of ions. So if we had something like Na plus, H plus, Li plus, Ca2 plus. When we have any of these positive ions by themselves, first off, if you're asked to write the formula for an ion, it does need to contain the charges. So there, we need to write the charges on each of these things. And we would just use the whole name of the positive guy. So this guy here would be our sodium ion. This guy here would be our hydrogen ion. This guy here would be our lithium ion. And this guy here would be our calcium ion. So the easy guy to name really is the positive guy. When you're dealing with an ionic compound, you simply just use the whole name of the element. So that's pretty straightforward. If it's positive, just the whole name. Yes, ma'am. It is, yeah. So for both type 1 and type 2, we're going to get into the specifics of each of those in just a second. But yeah, so pretty much any type of ionic compound, anytime you have basically a positive ion, it's always basically just the whole name of the element. As we will see, the difference between type 1 and type 2 is with type 2, we do have to add something else to the name. In type 1, we don't. But they both basically, for the main part of their name, is going to be just the element name, basically. Yeah. Other questions? Now, when we have negative ions, we do a little bit different. So O2 minus, H minus, Cl minus. For negative anions, we actually take the first part of the nonmetal name. So we take the first part of the element name. We do drop the last part, and we replace it with IDE at the end of it. So again, instead of oxygen, this then becomes the oxide ion. Again, IDE. Instead of hydrogen, this becomes the hydride ion. And instead of chlorine, this becomes the chloride ion. And once again here, if we were going to write our formulas like we're doing here, we want to make sure that we do include the charges. So if you're asked to write the formula for an anion, again, you do need to include the negative charges in this case. Something else that we talked about, I think, at the end of one of those earlier chapters, maybe chapter 4, was the idea that when we do put these ions together, so whenever you put sort of a positive ion and a negative ion together, the overall charge for the formula when they come together has to be 0. So again, if you took a sodium and a chlorine and put them together, you got +1, -1, gives us a compound formula there of NaCl. The actual formula, when you put those positive and negative guys together, should always equal 0. It should have no charge in the simplest way possible to get it to 0. That is also why, for example, when we're talking about saying something like this, if we put calcium and fluorine together, once again, that is +2, that is -1. So when we put them together, we do need one more of the -1s there, and that gives us a proper formula here of CaF2. A reminder that the number goes to the guy to the left, right? The subscript there. The reason for that is what we talked about in bonding, right? Remember that we do need the extra fluorine in this case to allow calcium to lose both of its electrons, right? And achieve that noble gas configuration like we did when we were talking about bonding. And that allows each of those fluorines, again, to achieve that noble gas configuration. So really it's the bonding aspect of it, like we talked about in the previous chapter, as to why when we put these ions together, we do need to get them to equal 0 in the simplest way possible. What that will essentially do is allow everybody there to achieve that stable electron configuration like the noble gases. And again, we want to get it to 0. As you can see again in those formulas, metal first, non-metal second, positive and negative comes first. Any questions on that there? Now, just a reminder as well before we go a little too far, let's go this way here actually. Let's do it here on this page. Just also a reminder that I believe something we talked about previously, but when things do make charges on the periodic table, and by the way, again, this occurs when basically a metal and a non-metal come together, as we talked about before. If you take anything from the periodic table and it's by itself, not really combined with anything, it does not have a charge. But really when a metal and a non-metal come together, that's when they both gain a charge. So everybody in group 1, again, forms a +1 charge. Everybody in group 2 will form a +2 charge. Go here, maybe. Everybody in group 3, but I'll be honest with you, it really is aluminum and pretty much who we're talking about, will form a +3 charge. Remember, we got like the staircase kind of coming down this way. So when we talk about group 5, we're really talking about the ones above the staircase, the non-metals. It will go -3. Again, group 6 above the staircase where the non-metals are, -2. Group 7 above the staircase where the metals are, -1. So it's pretty much +1, +2, +3, skip a group and go backwards 3, 2, 1, basically. Again, non-metals, as we talked about, based on their periodic trends, are typically the ones that will gain electrons and become negatively charged. And metals, right, are the ones that will typically lose their electrons and become negatively charged in this case. Now, in the middle right here, right, is our transition metals. And again, they actually will have a variable type of charge. So it depends who they're hooked up with, how many they're hooked up with, and they will have this sort of variable charge. There is 3 in the transition metals, not drawn to scale here, but somewhere around here, zinc, cadmium, hang a left there, the silver. And these 3 transition metals, even though, again, they are transition metals, actually do have fixed charges. So zinc and cadmium, both of these guys here will form +2 when they form a charge, and silver will form a +1 charge. So even those are kind of 3 exceptions to transition metals that even though they are transition metals, they will have a fixed charge. And when we talk about things having fixed charges, what that means is no matter what the situation is, that's their charge. It doesn't matter how many they hook up with of somebody else. It doesn't matter whatever the situation is. For example, if you had sodium, which is group number 1, it doesn't matter who you bonded to in terms of an ionic bond. It doesn't matter how many you need of sodium, how many of the other one you have. Sodium will always form a +1 charge. It's just fixed. It's always going to be that. And again, the reason for that is some of those periodic trends that we talked about. Sodium has, bless you, 1 valence electron, which means once you get rid of that 1 valence electron, you get into those core electrons. If you remember when we talked about ionization energy, once you hit those core electrons, it jumps outrageously high, and you don't typically remove those core electrons, and that's why it kind of has a fixed charge. Same thing with our group 2 and group 3. Transition metals, if you also remember what we talked about with periodic trends and sort of electron configuration is, they can have upwards of 12 valence electrons, right? Because they have the S's and the D's that they can use. And because of that, they can make a variety of sort of charges because they never get really into those core electrons because they have so many valence electrons. So they have a more variable type of positive charge because of that sort of situation. Bless you. As opposed to sort of our representative elements, which once they lose those valence electrons, the only thing left are the core electrons, and they're not going to lose those. So they end up with more of a fixed charge always that happens. So when we look at anybody else in the transition metal region, what essentially we got going on sort of, in all the rest of the area, also in terms of naming, below the staircase where things like lead is, PB, tin, you got some tin, some lead in this sort of area and places like that. Those guys also have a variable type of positive charge. So even though they're technically not transition metals, those sort of metals that are below the staircase where tin, lead, antimony, bismuth is, they are really named like transition metals because they have the same sort of ability to make a variable type of charge. So again, when we talk about sort of these guys who can make these variable charges, it's really the transition metals. And again, just to the right below that staircase where they're sort of named the same way and they have that sort of ability. Any questions on that there? Yeah.
So when you just spoke about our fixed charges, can you say that 2 and 3 also have fixed charges and the rest don't?
Yeah, so everybody in group 1 will be +1, everybody in 2 will be 2. In group 3, really, for the most part, if you look at group 3 on the periodic table, it's really aluminum that for sure is going to be +3. Some books will say gallium underneath as well, but occasionally it can make some other charges and the guy underneath as well. But what happens is kind of the boron's considered a non-metal in the sense of naming, and it's not really going to have a good pattern as the aluminum, which is a metal. And then below that, you kind of get into what I was just talking about, kind of that grayish area where they're still metals and they're not really transition metals, but they do have sort of the ability to make that variable charge. So we go kind of +1, +2, +3 for aluminum. We skip group 4 together because that's just a whole combination of everybody, basically. You got non-metals above, you got metals below the staircase, you got some semi-metals on the staircase. So there's no real good pattern in group 4. Then we go to group 5, and again, it is the non-metals like nitrogen and phosphorus we're talking about, which are going to be -3, that they're going to gain electrons. And then group 6 and 7, also those non-metals like oxygen, sulfur, selenium, and fluorine, chlorine, bromine, and iodine. So they will always form those charges no matter what the situation if they're in one of those sort of locations, in addition to the zinc, cadmium, and silver, which are the 3 sort of exceptions for transition metals. They will also, no matter who you hook up silver with, no matter who you hook up zinc with, always going to be the +2 or +1, depending on which one it is. Yeah. Other questions? All right. So obviously that's an important thing for naming as well. So let's get into that there. All right, so we talked about type 1 and type 2, that they are ionic compounds. So let's really talk about what is the difference between those two things. So once again, these are both ionic compounds. These are both means, because they are ionic compounds, that we have a metal and a non-metal. And pretty much one of the main things you should always remember when you're thinking about naming is if there is a metal involved anywhere, that is the most important thing that you should look at. That's really what's going to determine how you're going to name something. So again, if you see a metal involved, that is really what you should focus in on in terms of sort of the rules of what you should follow in terms of how you're naming it. So what is a type 1 compound? A type 1 compound is an ionic compound where the metal basically has a fixed charge. So those are only guys that can form basically fixed positive charges. And when we talk about that, that means that your metal, which is the important thing, is from group 1, group 2, group 3 are with those 3 transition metals. Silver, zinc, are cadmium. So as soon as you see an ionic compound where we see it's the metals from group 1, group 2, group 3, zinc, cadmium, or silver, that just locks in type 1 compound, and that also locks in how you should name it. So you actually, as soon as you figure that out, you don't have to go any further in terms of thinking about anything else. You could actually just roll right into the naming part of it, regardless of what you see in the formula or anything like that. You just can basically roll into the naming part. Type 2 compounds, again, it's the metal that's most important. And what the metal will be in this case, as opposed to up here where it has a fixed positive charge, the metal here will be a transition metal. Are just to the right. Again, under that staircase that we were talking about, where we were talking about kind of lead, tin, which is SN, and all those guys there. And what these guys have is that metal can have a variable positive charge. Now, when you identify a ionic compound as being a type 2 ionic compound based off of the metal, what that means is actually you have just a little bit more work you have to do before you could go into the naming. So it's not as straightforward and quick as you get a type 1. You could just simply name it. You do have to sort of figure out a couple of things. And what you really have to figure out, as we'll talk about, is what is the charge on the metal? And that's because it can be different types of positive charges. So something like chromium could be +2 or +3. Something like copper could be +1 or +2. It does actually depend on the situation for a type 2 metal as to what charge you end up with. So it depends on who they are bound to, how many of different elements they're bound to, as to what type of charge you get. And again, that is what's the difference between a type 2 and a type 1. Type 1, it doesn't matter who they're attached to. They're always just going to have this fixed charge. But type 2 metals can vary depending on the numbers of other atoms that are attached to as to what positive charge they're at. The good news, as we'll talk about, is it's not super hard to figure out what charge you're dealing with, but you do have to take that extra sort of step of figuring out, okay, what is the charge? And that's what you should think about as well when you identify that metal, which is the most important thing as being a type 2 metal. The first thing you think about is, okay, is a type 2 metal, it could have a variable charge. I need to first figure out what the charge is on it before I sort of proceed to the naming part. So that's the additional sort of thing you have to kind of think about. You don't have to worry about that with a type 1 compound. Any questions on that so far? All right. So here's a table from your book. And again, you can see if we have just the ions and we want to write the formulas for it, we have our positive guys, which we basically use our whole name of the element. All of our negative guys gets the IDE treatment. Once again, you can see here our favorite friend here, hydrogen, can kind of be an interesting one. It is actually one of the only elements that can kind of go both ways. It could be positive or it can be negative. And I would say probably most of the time, hydrogen will be positive. The one time where it will be negative is if it actually comes after a metal. So for example, if you had LiH, in this particular case, this is lithium with a +1 charge. And in this case, this is actually hydrogen with a -1 charge. This is what is known as lithium hydride, by the way. And again, we would use that negative version of hydrogen's name because it does come second in this particular case. Bless you. Hydrogen is also kind of a weird sort of element in a sense. We know from our conversations, right, hydrogen is a nonmetal, right? But in terms of naming, it actually, for most cases, will sort of act like a type 1 metal, even though it is a nonmetal. So for naming purposes, hydrogen kind of acts like a type 1 metal, even though, again, it is actually a nonmetal. So again, hydrogen has some unusual properties, and one of those properties is when we kind of name it, we do actually just kind of think of it a lot of times like a type 1 sort of metal. It's also why it's kind of hanging out over there in group 1, because in a lot of cases we kind of think of it like that as like a group 1 metal, especially with ionic compounds. But it's still a non-metal, but in terms of the naming aspect of it, it really does sort of work more like a type 1 than anything else. It is usually not named as a sort of non-metal sort of situation that occurs later on. All right, so let's talk about the official rules here of doing type 1 compounds. So once again, our type 1 compounds are our metal and our non-metal. And as I mentioned earlier, pretty much always should focus in on that metal. It's going to be one of those guys, as we just talked about, group 1, 2, 3, silver, zinc, or cadmium. And as I mentioned earlier, as soon as you see that it is a type 1 compound, you pretty much could just roll right into the naming. And how do you name these guys? We simply use the whole name of the metal. And the non-metal, again, we drop the last part of the name and we replace it with the IDE. Once again, it does not matter how many of everybody you got going on in this situation. It is pretty much just rolls right into that. So as we saw earlier, we had NaCl. If you are going to sort of look through this and try to name this, really, again, the first thing you want to do is go, sodium is a metal, chlorine is a non-metal. And once again, what that should scream to you is I am dealing with an ionic compound. And as we talked about, we want to always look at the metal. And when you look at the metal, you go, that guy is on the periodic table there in group 1, which should also scream to you that that is a type 1 compound. It has a fixed charge. And at that point, you should stop screaming at yourself. But and then you could just go right into the naming at this point, because you really don't have to figure out anything else at that point. Once you identify that metal as a type 1, you roll with the whole name there of our metal, which is sodium, and again, chlorine drops the last part and it becomes sodium chloride. Now, if you take the one like this, we have CaBr2. Once again, we would do the same sort of thing. That is calcium, which is a metal. That is bromine, which is a non-metal. Once again, you should know it's ionic because of that. We want to look at our metal, which is always the most important thing. We see our metal hanging out there in group 2. That then should tell you it is a type 1 compound because it is group 2. It has a fixed charge. That is all you need at this point. And then you would call this whole name of the metal calcium. If I spell it right there, calcium. And then bromine becomes bromide. So this would be calcium bromide. Again, it is the metal that's the most important. The one thing to answer the question you want to ask, which is, shouldn't I put di there because it makes it look fancier, and it will make it look like it'll have an X on it if you do that. You do not use a prefix here. So you never, ever, 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 one more time for good measure, ever use a prefix when there's a metal involved. So there's a time and place for prefixes, and this is not the time whenever a metal's involved. So the way you want to remember that is, if you have a metal, you should not be using prefixes for sure. And this very common mistake that people want to do is they want to use a prefix because, again, they make it, maybe it sounds more chemistry-like or something like that, but you don't want to do that. There's probably only a less than 1% chance you will ever have a metal and a prefix in the same name, or in the same sort of name for a compound. And that's because the actual second element has a prefix in the actual name itself. It's not because you put the prefix on, it's just kind of what you call the other guy. That's the only time you will ever see really a metal and a prefix together. And that happens when we talk about polyatomic ions a little later on in this chapter. But other than that, you'll never see it. So if there's a metal, you should not be putting a prefix. This is not dibromide. This is just bromide. It does not matter in a type 1 compound, or if you have a metal. If you got like 400 of the metals and 300 of the non-metals, you just still use whole name of the metal. Non-metal gets the ID. It does no effect on the name. The reason we have the 2 here is what we talked about earlier. The reason we have the 2 is, even though, again, this has no charge over all the formula, This is made up of a cation that has a +2 charge, right? And the bromine, which is the anion, is group 7, which has a -1 charge. Once again, the overall charge needs to equal 0, so everybody gets that noble gas configuration. And that is why we have 2 of the BRs there to balance out the +2 that's there. And that gets all 3 of those guys to that noble gas configuration through bonding and transferring of electrons. And that's how we get to this proper formula here that has no charge. Any questions on that there? So a reminder as well, as we just talked about there, even though we see ionic compounds, when we put them together, the cation and anion together to make the formula, it has no charge. It is still really made up of things that do have charges. So you want to remember that. So again, here we have Ki, and if we went through our sort of system, K is a metal, I is a nonmetal. So once again, that should get you to a ionic compound. And always a metal being involved is the most important. And again, we see that is a group 1 metal, which means it's a type 1 metal. And at that point, that's all we need. Again, as you can see on the bottom there, we're just going to use the whole name of the metal and our nonmetal going to get the IDE at the end of it, potassium iodide. Once again, this guy that has no charge is really 2 things that do have charges. And really, if this was in a solution, for example, they would be floating around by themselves, those ions, as they are strong electrolytes. They would just be floating around in a solution. Yeah.
Example, would we have to have
What's that? Iodine actually has a -1 charge. So when you look at that on the periodic table, it goes 1, 2, 3, all positives. Then you skip group 4. And then it goes actually backwards at that point, -3, -2, -1. Yeah. So it kind of goes, think about like going up to 3, 1, 2, 3, skip, go backwards, 3, 2, 1, backwards. Again, positives on the left there because they're metals, basically. Non-metals could be negative. Yeah. Other questions? Yeah. Balance the chemical equation? You will, yes. Yeah. Like in a reaction, is that what you're talking about? All right. Yeah. You will. So if you're asking, you will need to be able to put things together to write the formula for it correctly to balance it out. And you will also have to name it as well. That's right. Yeah. And again, whenever it's ionic, that's what you want to think about. Again, the simplest way to get those positive charges and negative charges to get to 0. And again, the simplest way you could do it, if you're not sure what way to do that is, you could oftentimes just multiply kind of the numbers together there, right? 1 and 1 is 1, so you just need 1 of each, right? Whatever the charge is, you can multiply them. And then you basically just need to get them both to that numbers and add up how many you have. And if it helps you like I do here, a lot of times when I teach this is I just draw it out like how many of each one you need, and all you have to do at the end is just count what you drew, right? It's like I got 1 K and 1 I, and that's what the formula should be. As opposed to like over here on the previous slide when we did this one, I have 1 Ca and 2 of those guys, so 1 Ca and 2 of the other guys. And again, that is, you can visually kind of see how many of each one you need if that helps. All right, so why don't you try some here, or why don't you name those guys? Actually, I think I might have did that one, so let me switch this one to maybe, let's do. Then why don't you also write the formulas for these? Let me just make some stuff up here. Let's go with, let's go calcium oxide. Let's do silver sulfide. Let's go aluminum. Let's go aluminum chloride. All right, everybody on the left there, proper names, and everybody on the right, proper formulas would be good. Maybe I'll add one more. Let's see. Let's do magnesium nitride. Okay, so let's take a look and see. So again, when you're going to name something, really identifying what you're starting with, like we talked about, is kind of important. So potassium is a metal and Cl is a non-metal. So we got a metal and a non-metal happening here. So again, as soon as you see that, that should go ionic for you and kind of check off that box. Remember that as we talked about, once the metal's involved, that is the most important thing there. And when we look at the metal in this case, that is potassium, which is group number 1 on the periodic table. That tells you this is a type 1 metal. It will have a fixed charge. And really, in that point, that's all you need to name this thing. So you could just roll into the whole name of the metal, potassium. And again, here we're going to go chloride with our nonmetal IDE at the end of it. This again, the cation, if you were asked to write the formula for the cation, it is K plus in this case. You would need to include the charge if you're asked to write the formula for the ion. And if you wanted the anion formula, it is in this case group 7 minus 1. That is why when we put it together here in our formula, +1 minus 1 equals 0. So we just need one of each of them in that particular case. Any questions on that one there? Coming here, we got zinc, which is a metal, sulfur, which is a non-metal. So that checks off the ionic box. It again is going to be the metal that's most important. In this particular case, the zinc is actually a transition metal, but it is one of those transition metals that has a fixed positive charge. So it is actually a type 1 metal because of that fixed positive charge. That again is all you need to name this. So we're going to zinc sulfide, that guy right about there. And that would be our proper name. Again, the cation in this case, if you were asked to write the formula, would be zinc with a +2 charge. And the sulfide would actually be sulfur with a -2 charge, as it comes from group number 6 on the periodic table. And again, that is why we have one of each of them. +2 minus 2 gives you 0. Coming to our next one, this is Mg, which is magnesium, metal. Non-metal for chlorine, checks the ionic box. Looking at our metal, which is magnesium, group number 2, fixed positive charge, checks the type 1 box. That means we could go right into our name, which is magnesium in this case. And again, chloride here. Once again, no prefix, as it is a type 1 and a metal's involved. So this would be magnesium chloride. The cation in this case would be Mg2 plus. The anion in this case is Cl minus, not Cl2 minus, right? The 2 means what? You have 2 of those, yeah, each Cl minus. So there is no Cl2 minus, which is sometimes commonly a mistake that people will write. It is just Cl minus. So when you're asked to write the formula for the anion or the cation, either one that has a charge, it should just be one ion by itself. So just whatever that one single ion charge is and formula for it. Any questions on that there? That is barium, which is a metal. That is hydrogen, which is a non-metal. It is ionic here. Barium is group 2, which means it is a type 1 metal. And that is all we need in this case. So this would be barium. This is actually the negative version of hydrogen. And this would be hydride. Again, this is barium, which is group 2 plus 2. And because hydrogen comes after a metal in this case, this is the time where it will be -1. And that is, again, why we have 2 there, because to balance out the positive charge, we will need 2 of those -1 charges. Yeah.
Which would write out the formula for hydrogen, for example, we have to write out hydrogen minus both times, or just one?
Oh, so if you were asked, for example, to write the formula for the anion, which I think is your question, you would just write one. Just like up here, you would just do one of those guys. It's sufficient. If you wanted to incorporate like the two, you would actually you could put the two in front of it and do something like you have two of these or something. But usually sufficient enough. You don't really need the two. You just need to write the formula for the one ion by itself. Usually, yeah. Other questions? All right. And by the way, that's not H2 in this case, like it's H2O2, N2, or diatomic or anything. Again, the two's there to balance out the charge. So that's not like, those type of things. All right. So when we look at the names and we want the formulas, what we want to think about is basically what we still have going on in terms of what we're dealing with. So again, calcium is a metal. Oxide is oxygen, which is a nonmetal. At this point, you should know it's ionic, and what that means is you need two ions basically to put together. So when you want to put it together to write the formula, you want to start with just the basic ions that make up those things. So calcium, which is group 2, plus 2. Oxide, which is oxygen, group 6, minus 2. Now we're ready to put this together like we've done before. Plus 2 and minus 2 is one of each of those. We'll get the job done in this case, a little CaO action. Here, silver is a metal. Sulfide is a nonmetal, so again tells us it's ionic. You need two ions. Silver, once again, is a transition metal, but it is one of those threes that has a fixed charge. So whenever silver is involved, it is going to be +1 always. And sulfide is group number 6 on the periodic table. That's going to be a -2. So again, to balance this out, we could see we need actually one more of the silvers in this case. And if it does help you to sort of just draw it like I just did at this point, all you have to do is count what you got there. 1 and 2 of them, so that gives you 2, and one of those, and now you have the right formula basically in this case. So I would highly recommend doing it that way, thinking about balancing out the charge. A lot of times people are taught this move of bring the charges down, bring the subscripts up type of move. And it works about 93% of the time. You will come across a lot of times where it will not work and we will get the wrong formula or maybe even the wrong name because of that if you just kind of blindly kind of move the things up and down. So it is really better to kind of think about it as balancing out the charges to make sure you do get the correct formulas. Or if you're okay with like 93% of the time being right, then just roll with it blindly and just kind of cross them over. But you definitely will come across a number of ones where you will get the wrong answer just doing it that way. So just keep that in mind if you see that or you're taught that by somebody. Again, it doesn't work 100% of the time if you just kind of cross them over. Here's aluminum, which is group number 3. And chloride, which is group 7. So again, that's a metal and a non-metal, so I know it's ionic. Once again, I'm just going to try to balance it out, and if you're not sure, just multiply the two numbers together. 3 and 1 is 3. So aluminum is already at 3. And the chloride, to get the 3, I need 3 of them. So now I just count what I got. I got 1 of those. And I got 1, 2, 3 of those. And now I have the right formula in this case, right? Which would be AlCl3. Lastly here, magnesium, which is a metal. Nitride, which is nitrogen, is a nonmetal, so it's ionic again. Magnesium group number 2 plus 2. Nitride group 5, which is actually a -3. Again, if I just multiply those numbers together, if I'm not sure what number I'm looking for, the common number is 6, basically. So I need to get magnesium to 6. So I need not 1, not 2, but I actually need 3 of them to get me to +6. For nitrogen, I just need 2. And now I can just count 1, 2, 3. I'll go up on top so I'm running out of room. I got 3 magnesiums and 1 and 2 nitrogens, right? Gives me my proper formula in this case. Any questions on the name or writing the formulas there? Yeah. Okay. All right, so that is type 1 compounds. Let's talk about type 2 compounds. And really the deal with type 2 compounds is it's still a metal and a nonmetal. It is still the metal, the most important thing here. But the metal here, once again, will have a variable positive charge. So this, again, is an ionic compound. Still metal and nonmetal. And once again, here it is this guy here that could have that variable positive charge. And again, that's going to be again, as we talked about, your transition metals, except for those three, zinc, cadmium, silver, and just to the right, where we're talking about now, tin and lead in that area below the staircase. So the difference here is when we have type 2 compounds, we still will use the whole name of the metal. We will still use the non-metal like we did previously with the IDE treatment. So the additional thing we have to do here when we name these guys is we need to lay up some Roman numerals. And the Roman numerals is the positive charge on the metal ion. So a super common mistake that people make is they think the Roman numeral tells them how many like metals they have or something like that. But it's actually if you took the positively charged guy out, just one of them by itself, what the positive charge would be on it. So it's simply not how many you have, but just took one of those positive guys out, what the actual positive charge is, the actual number of it. So why do we need that? For example, if we take a look at the one there, which is FeCl2, how should we approach this? We should approach this the same way as we approach type 1 and pretty much all naming, which is I see iron, which is a metal. I see Cl, which is a non-metal. That tells me it's ionic. I'm going to now look at my metal, and it is dead center on the periodic table in the transition metal region. And as soon as I see that, I should know it's a transition metal, and it is a type 2 ion, which means it has a variable charge. So the additional thing that you have to do here, like I said before, which is unlike type 1 where you could just roll right into the naming, you do have to kind of step back for a second and figure out what the charge is on the metal in this particular case. The very good news is you will always 100% of the time you will always know the charge on whatever that metal is attached to. So in this case, it's attached to Cl, and Cl is group number 7 on the periodic table, and we know that group number 7 has a -1 charge, right? In this case, though, we don't just have one of those Cl's, we have how many? We have 2 of them, right? So once again, that is -1, -1. That is a net of a -2 charge happening. Remember that the formula needs to equal 0, right? So to balance out that -2 charge, since there's only one iron, the iron here has to be +2 in this case. And again, that's how you could very easily figure out what the charge is. Now that I figured out the charge, now I'm at the point where I don't have to figure out anything else. We're just going to name it. This is iron. Roman numeral 2, once again, for the charge on the metal, not how many you have. And just like with type 1, because there's a metal involved, it doesn't matter there's 2 Cl's. We're just going to name it chloride. Again, no prefix here. Yeah, so don't prefix it up. You don't want an X or anything like that. Yeah. Question on that name. Why do we have to do that? Let's just say, for example, we have this guy, right? We had FeCl3, right? So we do our same sort of deal. Iron is still a metal. Cl is still a non-metal, which again tells us it's ionic. We look at our metal, which is still iron, which is a transition metal, which tells us it is a variable charge, so it's a type 2 compound. So we do our same deal here, but in this case, we have not 1, not 2, but we have 3 of them, giving us a -3 overall charge, which means in this case, the iron is not +2. The iron has to be +3 in this case to balance it out. And this would give us now iron, Roman numeral 1, 2, 3, again, for the charge that's on it. And again, it doesn't matter how many chlorides we got there. It's still just going to be iron 3 chloride in this case. So the reason we need the Roman numerals to tell people in the first case, we're dealing with the iron that has a +2 charge. And in the second case, we're dealing with the iron that has a +3 charge. The reason we do not need a Roman numeral for type 1 is no matter what the situation is, something like sodium is always going to be +1. So it's like a known thing. You don't need to tell somebody it's going to be +1 because it cannot be anything other than +1. That also goes for those three transition metals, zinc, cadmium, and silver. They also have those fixed charges, which is why we do not use Roman numerals with those transition metals, because again, they are more of a type 1, which has a fixed positive charge. Everybody else there will use Roman numerals, including things like lead that could be like +2, +4, tin, same deal. It could be a lot of variable type of charges. Any questions on that? Yeah. Yeah, so if you have the name, if you're asking if you're given the name, it should have the Roman numeral in it because it should be the correct name. So you would be given the correct name, which has the Roman numerals in it. And then yeah, you would work backwards, and that's how you would know actually when you're given the name, right? You see the Roman numeral 2 or the Roman numeral 3, you know which one you're dealing with. That way you could put back your formula correctly. So yeah, yeah. The only time you would have to figure out the charge of the iron is in a situation like this where you actually have the formula and you have to get to the name. But definitely, if you're given the name, it should be given to you properly, and in given it properly, it should have the Roman numeral in it. Yeah. Yeah. It will be all transition metals, and also again that staircase that starts out there where boron is, kind of coming down. Again, it will be below the staircase, just to the right, where you have things like lead and tin and bismuth and like antimony, those guys. Even though they're technically not transition metals, they also can have a variable positive charge, so they're named the same way as type 2 compounds. So it's pretty much everybody in the transition metal region except for zinc, cadmium, silver, which have fixed charges, those three. And then everybody to the right of the transition metals below the staircase, because remember, above the staircase, we're now into like non-metals, right? So kind of below the staircase, we still have those metals, and they have a variable charge. And I would say again, like the lead, the tin, that antimony, bismuth sort of area, that PbSN area, that's again outside the transition metals, where you'll still need to use Roman numerals. Yeah. Other questions? All right, so why don't you name this one here, see what you come up with. Speaking of lead, by the way. Okay, so let's take a look. So once again, when we look at this, we got Pb, which is a metal, O, which is oxygen, which is a non-metal. Once again, that should scream to you ionic. We're going to look at our Pb, and as we were just talking about, this is really not a transition metal, but it is one of those metals that are below the staircase and to the right that can have a variable type of charge. So that's going to tell us it's a type 2. So in this case, we're not sure what the lead is, but we do know we have oxygen, which is group number 6 on the periodic table. And guys, in group 6 has a -2 charge. And there's not just one of them in this case, there's actually two of them. That gives you a -4, which means in this case, this is actually lead with a +4 charge. This is not lead 2 that you get when you just go switching them around, yes? So this would be one of those examples where if you just kind of blindly move the charges or subscripts up, you will get the wrong answer in this case. So again, it doesn't work 100% of the time. And at this point, that is lead, Roman numeral 4, because of the charge. And again, it doesn't matter, we have two of these. This is just going to be oxide, no prefix, because a metal's there, right? So we're not going to use any type of prefixing there. Any questions on that? So again, a good example of don't just blindly do it because it may not always work out correctly. Yeah. Any questions on that one there? Now, there is a older system of naming these sort of type 2 metals, and we're really not going to use it pretty much in this class, but just to give you an idea of that other way of naming, they will end with ic or ous, the names, and they will not use Roman numerals. So the positive ion that has the larger charge will end in ic. Like you ate too much, it feels icky, right? That's a good way to remember that. And the one that has the lower positive charge will end in OUS. And they'll also use, in this case, kind of like the old school name for the element. So instead of iron, for example, they may call it ferric chloride for +3, or they may call it ferrous chloride for +2, iron in that case. Same thing with copper, cupric and cuprous is used. So even though these are sort of historical type names, it's used a lot. They actually still use for copper and iron a lot those names instead of the Roman numerals. But for here, we will strictly roll with Roman numerals. We will not use the older name. But you still sometimes do see, especially like I said, iron and copper, very common. Sometimes people, when they write papers or things like that, they'll kind of roll with the kind of older way of naming it, cupric or ferric or ferrous in that case. And here's sort of a table from your book that kind of shows you the difference here. Higher positive charge, lower positive charge, ich and us. Higher positive charge, lower positive charge, ich and us. And again, you can see also they kind of roll with the little kind of older type namings for each of these sort of elements. The one sort of type 2 metal that really screws up people a lot is right here, our friend mercury. And mercury like this and mercury like this are two different mercuries. This one here that oddly has a lot of 2's in it is mercury 1, Roman numeral 1. And the one that has just the 1 2 in it is mercury 2. And that is because mercury 1 comes as a dimer, basically not drawn perfectly, but it comes basically as 2 1s stuck together. And that's why overall it has a +2 charge because they're each 1. And overall why there is a bottom 2 as well, because there's 2 of them stuck together basically. So oddly, mercury is kind of a weird one. When you see the most 2's, then it's actually mercury 1. And when you see just 1 2, it's actually mercury 2. How do you know when you're dealing with it in like a formula, if you're dealing with mercury 1 or mercury 2? The 2 on the bottom tends to still be there when you see it in the formula. So for example, if I had this guy versus this guy, this one here is mercury 2 oxide. And that is because there is no 2 on the bottom there. That's basically Hg2 plus O2 minus. Here you can see the 2 on the bottom hangs out, and this is actually mercury 1, and that is Hg2 2 plus and O2 minus. So like I said before, that 2 on the bottom tends to hang out there in the formulas, and that's a good way to know if you're kind of dealing with the +1 or +2 version of it. And again, oddly, the one with all the 2's is the 1 version of it, while the one with the 1 2 is the actual 2. Any questions on that one there? So once again, in this class, and pretty much most of your chemistry classes, we will always roll with the Roman numerals. But as I mentioned before, sometimes these older way of naming, especially with copper and iron, are very common. They still kind of use them. All right, so as we've been talking about, we go whole name of the metal. We Roman numeral for the charge on the metal. And then we go our nonmetal IDE again. So pretty similar to type 1. The additional thing you have to do is just sort of figure out the charge on the metal. And once again, you should always know the charge on whatever it's attached to. So you just kind of want to work your way backwards to figure out the charge on the metal. All right, so why don't you try some here, and I'll give you some names as well. Let's do iron 3 oxide. Let's do nickel 4 chloride. Go tin 2 phosphide. All right, so names on the left and proper formulas there on the right. Okay, so let's take a look here and see how we're doing. Um, Actually, we'll take a break, actually, I think.